line, position versus time graph, what's it tell us? It tells us the velocity, okay? So the slope of the line tells us the velocity of the motion, okay? Anytime we've got a straight line on our graph, it's the same equation as y equals mx plus b. We're not going to have to use that a whole lot. We don't need to use the slope of the equation of our line a whole lot. But what we do use a lot is the slope, okay? And we know how to calculate slope? Yeah, change in y over change in x, or rise over run. That's how we're going to calculate slope a lot here. So I want you to take a look at the graph that's listed on your slide and tell me, if I was going to calculate the velocity of that particular graph, what would my units be? Oh, it's kind of hard to see on yours. Sorry. Can you see it? What would the units be if I were going to calculate the slope of my graph? Centimeters per second. So although most of the time we want our velocity to be meters per second, there could be times when our graph gives us a different unit. So make sure you're watching that carefully here to calculate slopes of that line. Okay, so that is position versus time. What happens on a position versus time graph if my line is horizontal? It's stopped. It's staying still because my position right here is unchanging. And so if my position is unchanging, that means that I'm not moving anywhere. Not going forward or backward or anything. I'm standing still. Okay, so now we're going to look at a different type of graph, okay? The first graph is what we've seen, a position versus time graph. And if we see a straight line here, that means we have constant velocity, right? A straight line in any direction means constant velocity. So even if I had a straight line that looked like that, that would mean constant velocity in what direction? Forward or backward? Backward. What if my line looked like this? Would I have constant velocity? Yeah, but what would it be? 0, right? It's still constant, but it's 0. So any sort of straight line gives us constant velocity. But now we're going to look at a second type of graph called a velocity versus time graph, where velocity is now on the y-axis and time is still on the x-axis. And so if I have constant velocity on this graph, it's going to be a straight line. Okay? And now on this type of velocity versus time graph, a horizontal line doesn't mean we're stopped. It means we have no change in velocity. It means we have our cruise control set. Right? It means we're moving at the same speed for that length of time. Does that kind of make sense? So we've got to make sure we're really in tune with what type of graph are we analyzing. Is it position versus time, or is it velocity versus time? Because that changes the way we think about what's happening in the motion. Okay, so today our focus is going to be learning more about velocity versus time graphs. Okay, so if we've got non-constant velocity, if we've got objects that are speeding up and slowing down, it's even more complex motion than before, and it requires a velocity versus time graph. So let's talk about what's happening from point A to point B. What's happening from point A to point B? Are we moving forward? Are we moving backward? Are we speeding up? Are we slowing down? Are we staying the same? We are speeding up, I would agree, right? Because we go from a velocity of 0 meters per second to a velocity of 20 meters per second. Okay, so we are speeding up in the positive direction. How do I know that I'm moving in the positive direction? Because my velocity is going from 0 to positive 20. The only time I would be going in the negative direction is if my velocity were below -5, -10, negative 15, right? If my velocity were below the x-axis, that would tell me I was moving backwards. Okay, so let's walk through a little bit more of this graph so we can talk more there with that. Okay, from B to C, what's happening? I'm constant velocity. I'm not stopped, but I've got cruise control set, right? So I'm moving at a constant speed or a constant velocity of 20 meters per second. From C to D, what am I doing? Speeding up, still moving in the positive direction. From D to E, constant velocity, right? Or cruise control. Then from E to F, what am I doing? I'm slowing down. But what direction am I still moving? I'm still moving forward. I'm still moving in the positive direction. Okay? And I know that because my velocity is going from positive 40 to positive 20. So I have the brakes on. I'm not moving backwards. right? On a position versus time graph, this would have told us we were moving backwards, but it does not in this case, right? I'm going from 40 to 20. Okay, from F to G, I've got cruise control set, and then from G to H, what am I doing? I'm speeding back up, but I'm still moving in the positive direction, okay? So in this whole graph, I'm moving in the forward direction the whole time, right? I speed up, then I set my cruise, then I speed up again, then I set my cruise, then I slow down, then I set my cruise, and I speed up again, right? But I'm still moving forward. That's really important, okay? The only situation in which we would be moving backwards is if we were underneath the x-axis. That would give us a negative velocity, right? Or a backward velocity, okay? So let's talk about on velocity versus time graphs, what is different. The slope on a velocity versus time graph now tells us something called acceleration, and that's kind of a new term for us. We haven't really talked about acceleration or how to calculate acceleration yet, but acceleration is what's going to be calculated from the slope of the line, okay? So if I'm looking at the slope right here, I am speeding up in the positive direction. That would mean that I'm accelerating, right? And I need you to know that acceleration, maybe write this out separate. Acceleration is any sort of change in velocity. So any change in velocity is considered an acceleration. Now, is that different from what kind of you think of as the definition of acceleration? What do you think of when we say acceleration? You automatically think of going faster or speeding up. And that's true. That's a part of acceleration. But in its most basic definition, acceleration is just a change in velocity. Yeah, we can use decelerate to tell us that we're slowing down. That's fine. But when we calculate acceleration, it can be both positive and negative. Okay, and we're going to talk about what positive and negative acceleration means here in a minute, because it doesn't always mean that a negative acceleration is slowing down. And that was a little tricky for us, okay? Acceleration doesn't always mean that the sign matches the speeding up or the slowing down like it does with velocity. So I'm going to walk us through that here in just a minute. Okay, on the rest of this graph, I want you to tell me what's happening from here to here. We're slowing down to what? A stop, because here 0 meters per second, right? The x-axis is where I'm stopped. So here I'm slowing down in the positive direction, but from here to here, what am I doing? I'm speeding up in the negative direction, right? So I'm like moving forward, I stop, and then all of a sudden I speed up in reverse. That's what's happening in that little segment of the graph right there, okay? It could also be that something's rising in the air, right? As an object's moving upward, it's slowing down until for just a second it comes to a stop, and then it falls back to the ground and it picks up speed as it goes downward like that. That could also be an example of what that graph would look like. Okay, but this little segment of my graph means that I'm slowing down to a stop, and then I'm speeding back up in the negative direction. Okay? And then from here to here, what's happening? I'm slowing down in the negative direction. Okay, I'm going from negative 2 meters per second to negative 1 meters per second. Okay, sometimes it's difficult for us to really see it based on trying to remember this line's positive, so what's that mean? And this line's negative, so what's that mean? If you're in doubt, just go read the numbers on the axes, right? I'm going negative 2 meters per second, and now I'm going negative 1 meter per second. That has to mean that I'm getting slower, right? Because what's negative velocity tell us? It just tells us the direction, okay? So when in doubt, just kind of check those numbers on the y-axis there. All right, next question I'm going to ask is, how can I determine displacement from a velocity versus time graph? Is there a way for me to determine displacement, how far I've gone? Okay, the way we can do that is by calculating the area under the graph. The area under the graph. And I want to make another little clarification here. Area under the graph to the x-axis. Okay, so it's only to the x-axis. So let me explain what that means. If I wanted to find out how far we've traveled from 0 to 4 seconds, right? I know during that time I sped up, I set my cruise control, then I slowed down, but I moved in the positive direction that whole time. If I want to find out how far I went, I need to find the area under the graph to the x-axis. So I need to find the area of that shape right there. Okay, do you see it? Is there an easy way for me to do that? Is there one equation that can give me the area of that shape? What did you say? 5 what? 5 is the area, you think? Okay, but can I do it in one equation? That's what I'm asking. I don't think so, right? That's not a trapezoid that I can do in one equation. So I'm going to split it up into manageable shapes. Find the area of this, the area of that, the area of this, and I'll add them all together. And that will give me the area of my space under the graph. That would tell me my displacement during that time. Okay, so let's go ahead and do that. The area of this first triangle, what's the formula for area of a triangle? 1/2 base times height. So this side has a value of 2. This side has a value of 2. So that would be 2 times 2 over 2, which means I moved during that part of my motion 2 centimeters. Okay, during this second of my motion, I'm at a constant velocity of 2 meters every 1 second. So that means I traveled 2 centimeters, during that time. So 2 centimeters and 2 centimeters. And now area of this triangle would be 1 times 2 over 2, which would be 1. So that means I traveled a total of 5 centimeters during that time. Okay, does that make sense how I solved that? Split them up into manageable shapes and then calculate your area. Okay, any questions with that? What if I asked you for the displacement from 4 to 7? Okay, I've got a couple different shapes there, right? I've got a triangle there, and then I've got to figure out how am I going to get that done, right? I can come up with a couple different shapes there, and then just find your area of that. We're not going to calculate that, but I want you to see how you can start to put that together. But remember, it stops at the x-axis. Okay, so you're not going to if I asked you for the area under the graph, you're not going to take this whole spot, right? One last thing, if I asked you to calculate this area, it would be negative because I'm moving in the negative direction there. So my displacement would also be negative, right? I'd be moving backward. Okay? All right, displacement from 4 to 5 seconds. Oh, okay. If I wanted to do just 4 to 5 seconds, I would calculate the area of that triangle. But it would need to be negative. So I think negative 1 meter probably during that. Yeah. All right. I'm not going to go over that part again. All right. We know that the slope of the line gives us the acceleration this time. All right. Give me the displacement here from 5 to 8 seconds on your graph. 5 to 8 seconds. So 5 seconds is at point D, and 8 seconds is at point E. This side of my rectangle is 40, I think. So 40 times 3 is 120. That's what I got. Yeah. You could also just look at your graph there for these easy rectangle, right? I'm traveling 40 meters per second for 3 seconds. So you can just multiply that and do the math too, right? Velocity equals displacement over time. You could look at it that way also. Okay. I want you to try the next couple here. Let's do these together just so we have one example together, okay? What's the acceleration from 0 to 2 seconds? So how would I go about finding the acceleration? What do I need to solve for? The slope, okay? So acceleration is slope. Okay, so from 0 to 2 seconds, you need to pay attention to how the x-axis is marked, right? It goes every 2 seconds. It's not going every second, it goes every 2 seconds. So that means the side of this triangle is 2. The side of this is 2. So that means what's my displacement? 2 meters. This one is meters. Right, because my velocity is measured in meters per second. What'd you say? It would be 2 times 2 over 2. So, yeah, that's where I get my 2 meters from. Yeah, that's what we're doing here. Displacement is area of that triangle. Oh, whoops. You're right. Slope. Okay. Up 2 over 2 would give me a acceleration of 1. My bad. Thank you. Okay. Units for acceleration are meters per second squared. Yeah, sorry about that. I don't know what I was doing. Okay. Units for acceleration are meters per second squared, because what it looks like if we're taking rise, that's meters per second, over time or run, meters per second is the same as meters per second squared. So my slope here, or my acceleration, is 1 meter per second squared. Okay, because I went up 2 over 2. All right, my displacement from 8 to 10 seconds. All right, now is when we solve for the area, sorry. Displacement from 8 to 10 seconds would be here to here. So that means I'm going to find the area of that triangle. It just goes to the x-axis. Just goes to the x-axis because here's 0. Okay, so that's 2. This is 2. So my displacement in this case would be 2 meters. Okay, last question here. What's my velocity from 16 to 18 seconds? We didn't talk about how to solve for velocity, but what do you do with this graph? If I'm asking for velocity from 16 to 18, that's here to here. Yeah, all I have to do is read the graph. I don't have to solve anything here. It's constant velocity, so it'd be negative 2 meters per second. Okay, do we feel pretty comfortable with defining each of those things on our graph? Okay. All right. The last thing I want to show you with acceleration is what does acceleration look like on a position versus time graph? Because we're going to do some assignments today that include analyzing both types. And I want to show you what this looks like. So there's 4 different ways acceleration can look on a position versus time graph. But I want to draw them and kind of see what you have to say. So let's say I'm on a position versus time graph, and I've got a slope that looks like that. I've got a curved line. Okay, my line is curved. Did I put these in after I printed it? Yes. Okay, sorry. Just maybe draw these out like at the top or the bottom of your sheet, because I want you to have these examples. I must have added this slide after I printed yours, so I apologize. So what would my scenario be? Talk me through what my motion would look like here. Am I speeding up? Am I slowing down? Am I going in the positive direction, negative direction? What do you think is happening here? Speeding up gradually. Okay. It is moving. Tell me first, are we moving in the positive direction or the negative direction? We're moving in the positive direction. Because my slope is generally in the upward direction. That's how I know that. Now, am I speeding up or am I slowing down? Because a curved on a position versus time graph gives us acceleration. Okay? Anytime we have curves on a position versus time graph, it means that we are accelerating of some sort. We have a change in velocity. So do you think I'm speeding up or I'm slowing down here? Any ideas? I'm speeding up. Okay? So I'm speeding up in the positive direction. And here's how I know I'm speeding up. I'm starting with a really shallow slope, right? And as I move, my slope is getting steeper and steeper, which means my velocity is increasing as time goes on, right? I start with a really low velocity, and as time moves on, my velocity gets steeper and steeper. So that's how I know I'm speeding up. What if my graph looked like this? What if my graph looked like this one up in the upper right? Am I moving in the positive direction or the negative direction? I'm moving in the positive direction. And do you think I'm speeding up or I'm slowing down? I'm slowing down because I start with a really steep slope, right? I'm moving fast. Now I'm moving slower, not moving very much. right? Do we see how that curve kind of shows us for speeding up or slowing down? Okay, what if my graph looked like this? What would that tell me I'm doing? I'm speeding up. In what direction? The negative direction. I'm speeding up in the negative direction. Okay, because I'm starting with a shallow slope. Negative direction because my slope is generally pointed downward. Right, so that tells me negative direction. Okay, and the last version of that graph would look like this. Right? This would mean that I am slowing down in the negative direction. Slowing down in the negative direction. Do we have questions about any of those four? Can we kind of see what that looks like?